In this video, number 7 in the series, I want to talk about the uh, interaction between light and atoms. Most of what we know about the natural world comes to us uh, by way of light. Light gives us the information if we know how to decipher it. And for each of the atoms or each of the elements that we're investigating, light serves as a window into the structure and behavior of atom. I hope I'll show that to you as we proceed. These are questions to consider when we are discussing the nature of light and how it interacts with atoms. Why do we get different colors from different materials, whether it's elemental or compound? That's a worthwhile question to pose. Why do different chemicals give us different colors? Here we see examples. These are all different elements that in a flame are giving us different colors. The understanding how this happens is a way of understanding how the atom is constructed. Now, some chemicals will give you different colors. If you put the chemical in a flame, it'll give you a different color if you put it in aqueous solution. And there's a chemical explanation for that. And classes of chemicals will give you roughly the similar colors. If we look, for example, at the red color of the red blood cells, they're called red blood cells because they have hemoglobin in them, and the hemoglobin has iron in it. And when iron combines with oxygen that it picks up in your lungs, it turns bright red. It does that because of the addition of iron into that structure. Here's another example. This is also red. The color that forms in the shells of crawfish and lobsters and crabs is what's known as a carotenoid pigment. This particular one that the structure is showing you there is called astaxanthin. It gives you a similar color, red, to the oxyhemoglobin, but for a different reason. All right. Light, in scientific terms, is called electromagnetic radiation. That's because light has an electrical component and a magnetic component. And we're not going to go into those details, but that's why it's given that name. This is one of the ways that energy travels through space. One of the primary ways that energy travels through space. It also travels through space as accelerated particles. In order to describe light, we need 3 variables. 1, the wavelength. Wavelength is the distance between 2 consecutive peaks or troughs in a wave. So we can simplistically draw a light beam as being a wave like that. Now, in reality, this is only, say, the electrical component. The magnetic component will be 90 degrees to that. The distance between these 2 peaks right here is a wavelength. And it's designated with the Greek letter lambda, the small Greek letter lambda. The other descriptive term we can use for light is the frequency. And it's given the Greek letter nu. Um, Very often, though, to avoid confusion with people who aren't familiar with Greek letters or uncomfortable using them, we will also be given just a small letter F for frequency. So you may see it both ways. What we're saying with frequency, though, is that if you position your eye here, then frequency is the measure of how many waves pass your eye in 1 second. So we could say it's cycles per second is nu, is the frequency. Okay. The last term, the third term, is speed. How fast does the wave move? In other words, if we take this position here and we count how long it takes for that peak of the wave to go from here to some distance and convert that into a distance in meters, a time in seconds, we get this value, which is given the letter C, 2.9979 times 10 to the 8 meters per second. Now, I don't want to get into too much detail or bog down in the various theories about whether light actually does travel at a speed. For our practical purposes, we're going to assume that light has a speed associated with it, and this speed is through a vacuum. The speed will change depending on the medium through which it's traveling. This speed is close enough to the speed in air, although various densities of air will cause it to change directions, and we might be able to talk about that in a minute. All right, these three terms then are used to describe the nature of light or describe the behavior of light. And these three terms are related to one another through this formula. Right? Speed of light equals the wavelength times the frequency. Now, what I like to do with my students is called dimensional analysis. Look at the units of measure, right? The units of measure for speed, meters per second. What's the unit for wavelength? Well, a wave is so many meters long. So this unit would be meters, correct? And the frequency is cycles per second. Cycles is actually not a unit of measure for anything. The unit of measure is really reciprocal seconds. So meters times inverse of seconds gives you meters per second. And that's one way of confirming that the equation is properly presented. But we can tell from this relationship, the speed of light is considered a constant. So these variables, when they multiply by each other, must always equal that constant. So that means if the wavelength gets longer, the frequency has to get shorter in order to keep this constant. When you multiply these two together, they can't both go up or you'll lose your constant. So if one goes up, the other one goes down, and vice versa. This is called an inverse proportion. And this is just a representation of what the wavelengths look like and the relationship of the wavelength to the frequency. So the frequency is 4 cycles per second here. Another unit of measure for this is called hertz. So reciprocal seconds is equal to hertz. So the wavelength is this amount for 4 cycles per second. If we shorten the wavelength, then if we make the wavelength smaller, the frequency gets bigger. So this one is 8 hertz. This one is 16 hertz when the wavelength is cut in half again. What we see in this slide is a representation of the electromagnetic spectrum. This is every possible wavelength that we have ever discovered anywhere in the universe. It goes from the very shortest wavelength on the left of the screen to the very longest wavelength on the right of the screen in terms of meters. So the very short wavelength is represented by gamma rays. And then a little bit longer wavelength is X-rays, longer still is ultraviolet. Then we get the visible range. And then longer than the visible range is infrared. And then microwaves, and followed by radio waves. That covers everything. The part that we can see with our eyes is a very narrow band of wavelengths between 4 and 7 times 10 to the minus 7th meters. The red wavelengths are longer than the blue wavelengths. And if you've ever had a science course before, you probably have been taught this mnemonic. All right, Roy G. Bibb. This is red, orange, yellow, green, blue, indigo, and violet. Okay. So let's move on. One thing we can equate with wavelengths or frequencies for that matter is the equivalence of light in terms of how much energy does it carry. And this electrified pickle is trying to demonstrate that as we put a direct current through that pickle, we are releasing some of that energy. The electrical energy is making heat. And as it heats up, it starts to glow. And we're turning some of that energy into light. So all of these energies, the total energy that's going into this pickle is not lost. It's just converted into different forms of energy. And one of those is light. And one of the fundamental principles of physics is that energy is conserved. In fact, that's the first law of thermodynamics. The total energy in the universe is the same as it was when it started, and it is now. All right, let's look at a little bit of history. And the reason I want to bring up these people is because the fundamental contributions that they made to understanding understanding light and its relationship to atoms. James Clerk Maxwell was a master mathematician. And in the middle of the 19th century, he came up with these series of equations, wave equations, that thoroughly described electromagnetic radiation. And they're still valid today. And they are based upon the understanding that light is a wave. Now, we're going to find some evidence that contradicts that in just a few minutes. But at this time, light was considered a wave and nothing else. I will say, parenthetically, that at the beginning of the 20th century, around 1900 and after, scientists generally believed that the universe was fully explained, especially with Maxwell's equations. And all that was left for them to do was to just refine our understanding. They could not be more wrong. Because about the same time, the beginning of the 20th century, a scientist by the name of Max Planck was studying a phenomenon called black body radiation. What we mean by black body radiation is it's like you take a chunk of coal and without burning it, like putting it in an inert atmosphere, and you heat it up. And the hotter it gets, it goes through an emitting light of different frequencies. And the hotter you get it, the shift goes from red through green, yellow, all the way to blue and violet. So the temperature at which this black body finds itself is an indicator of what color of light you can expect to get from it. That's black body radiation. And that phenomenon is used even today to measure the temperature of various stars. Like red giant stars are considered cool. White dwarfs are considered very hot, and so forth. Well, while Planck was investigating black body radiation, he came to the realization and he developed this equation where he equates the energy of the light that's being emitted is proportional to its frequency. So he said energy is proportional. Actually, it goes like this first. It's proportional to frequency. And then to make it equivalent to frequency, you need a conversion factor. So he said, this is it. And this is known as Planck's constant. So if this value, frequency, is going to be in terms of reciprocal seconds or hertz, then this Planck's constant and energy unit is going to be joules, right? Then this Planck's constant must be joule seconds for its units, so that seconds will cancel, leave us with joules. The value, you don't have to memorize the value, but I'm going to put it up here anyway. What Planck had discovered was the quantum nature of light. In other words, light is transmitted in packets. We call them now photons. Right? And if you're a fan of Star Trek, the original series or the movies, you'll remember that one of their weapons was a photon torpedo. I don't know how they constructed something like that, but they they got the name from this concept of the quantum of light, which is a photon. Well, what we're getting at here is that light now is considered not just a wave, but it's starting to acquire some character of a particle, like an electron, like a proton, a photon. All right. If we need to, this is frequency, HF or H nu. Well, since we know that this relationship is true, right, then we can solve our equation for that, and we get C over lambda. And if we substitute this in here, then we get an equation where we have Planck's constant times C over lambda. Right? It's just math, algebra, actually. There's Planck's constant. The only significance that this number is that it's the one that fits the equation and equates energy in joules to frequency in hertz or reciprocal seconds. Now, here's another piece of evidence that came to light at the beginning of the 20th century. It's called the photoelectric effect. And not to go into too much detail, I'll just say that it's observed among metals, elements that are metals. And if you have the surface of the metal here, right, there's your surface, and you have light here with its energy, right, strikes the surface of the metal. If that photon has enough energy, then it can eject an electron. If it has less than that energy, we call the threshold energy. If it has less, then it will not eject an electron. Now, there's a whole discussion we can go into, the controversy between wave nature and particle nature, but we don't have time to do that. So I'm just defining what the photoelectric effect is. What this is suggesting is that light behaves as a particle sometimes, right? These are the things that we observe in the photoelectric effect. No electrons are emitted by a metal below a specific threshold frequency, which is equated to energy by Planck's equation. Of course, the radiation must arrive at the surface of the metal in discrete packets or photons in order to make this phenomenon occur. Below that threshold frequency, no electrons are emitted. Now, the energy is not wasted, right? The energy, instead of ejecting an electron, is absorbed by the metal and heats it up. These are called thermal photons. Right? If they don't have enough energy to eject an electron, then they just heat the things up. All right, this minimum amount of energy is required to eject an electron. And I mentioned thermal photons just now. All right, continuing. The number of electrons ejected by light that exceeds the threshold frequency or the threshold energy increases as intensity increases. Right? There's no added energy per photon, but there are more photons of that energy striking the surface. So that intensity just means that we're ejecting more electrons because we have more photons. Not because there's more energy in the light, but because there are more photons of that particular energy. And they impart the threshold energy is required of the photon. And if the photon has more energy than's needed, then that extra energy is given to the electron as kinetic energy. Right? Any extra energy accelerates that electron to a certain velocity, which represents the kinetic energy. All right. Let's see. Those are all the important points. So what we can conclude from what we've learned from the photoelectric effect is that the interaction of light and matter happens with the electrons. That's where the business of light and matter happens, with the electrons. We can also say that the photon has a certain amount of energy and is tuned to the energy required for the electron to move uh, from one level of energy to another surrounding the atom. And we're going to talk about that a little more in just a minute. When we say it's got enough energy to leave the surface, we're saying it's going from the atom, energy level in the atom, to infinity. It's leaving the atom. Okay, I mentioned that already. All right, then Albert Einstein first mathematically described and proved the photoelectric effect. So he got a Nobel Prize for that. He also came up with this theory called the special theory of relativity. This one came first. He followed that later with a general theory of relativity. But the special theory of relativity proved mathematically that light has mass. Right? The famous equation, E equals mc squared. In other words, we can equate mass to energy. They're interchangeable. And the constant that's multiplied by mass to make this relationship work is the speed of light. Now, proposed um, Einstein proposed this theory of special relativity and the equivalence of energy and mass. That was theoretical. And then Arthur Compton came along and confirmed it experimentally. So now what we have staring us in the face is light that sometimes behaves like a particle, sometimes behaves like a wave. So which is it? Right? Both are correct. In fact, light behaves as both at the same time. That's just the nature of science. When the evidence stares you in the face and you have no other option, you have to accept what it's telling you. Now, we can take advantage of the wave nature of light or the particle nature of light through various mechanisms. One of those is called diffraction. Diffraction occurs when light encounters an irregularity in the surface. In this case, we're trying to keep it very simple. So what happens is this wave is impacting a block, and the only point that light can get through is that little pinhole right in the center. So what happens is that pinhole serves as a point source for a new wave. So the wave emanates from that point out in a circle. And we see the representations, light and dark is peaks and troughs. That's diffraction. Refraction is the bending of light as it passes from one medium into another. So when light strikes my lenses here, it's bent so that it focuses for my aging eyes. That's refraction versus diffraction. That has to do with the wave nature. And the particle nature, of course, is demonstrated by the photoelectric effect. Now, what does this have to do with atoms? It tells us an enormous amount of information can be gained about the atom based upon its spectrum. In other words, when we excite atoms through heat or electricity, any type of energy, then they get excited, and when they relax, they give up their energy in forms of light. And we can use that information to tell us something about the structure of the atom, actually the structure of the electrons around the atom. So we're going to focus on the very simplest element here, hydrogen. When hydrogen is excited and it releases its energy, it doesn't release its energy as white light, as a continuous spectrum. It releases it as a line spectrum. In other words, discrete colors, lines. So what does that mean? I think I've got a video.
The discharge tube is filled with hydrogen gas. When a high voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra due to the appearance of bright lines. In the hydrogen emission spectrum, there are four lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Try it again. Okay. So what we're saying is the line spectrum is telling us how the electrons are behave surrounding this one proton in the hydrogen atom. So energy levels are given numbers. The closest one is energy level 1. Next is 2, 3, 4, 5, 6, all the way out. And if an electron starts out at 6 here, and it drops to a 2, it gives off energy of the shortest wavelength, 411 nanometers. But if it goes from 3 to 2, it gives off energy of 656 nanometers. That's a longer wavelength. Short wavelengths means higher energy. Longer wavelengths means lower energy per photon. And the distance that the electron jumps, and notice there's no in between. It can only live at these different levels. So the bigger the jump, the shorter the wavelength, and the more energy that it gives up, because it's come from this higher energy to this lower energy. okay, and the others in between. Notice that they're all jumping to level 2. If they jump to level 1, they give up energy in a region that we can't see, right? So the visible spectrum is not the only one. There are parts of the spectrum that we can't see. All right. The significance of this observation is that only certain energies are allowed for the electron in the hydrogen atom. And for that matter, for any atom, only certain energies are allowed for jumps. What that does is this is kind of like a fingerprint, right? Hydrogen gives up this energy at these various wavelengths. And if we detect that in a sample in the laboratory or in an atmosphere around a heavenly body or from a star, then we can infer that that element is present at any one of those locations. That's why we say the energy is quantized. It only occurs in certain quantities. And when that electron jumps, it gives up one photon at this wavelength, and that photon has that much energy. I've been using a unit of measure here that I didn't define, the nanometer. So what is a nanometer? Well, nano as a prefix means 10 to the minus ninth. So a nanometer is 10 to the minus ninth meter. So when we say 410 nanometers, or was it 411? Well, I put 410. We're actually saying 4.1 times 10 to the minus seventh meters. Those are equivalent distances using different units. All right. I mentioned why the fact that light is line spectrum and not white. That is reference to the electron jump and the fact that electrons move in certain quantities only. If the levels were not quantized, then the electron could move at any position in between here, stop, give up light. If that were the case, then it could give up the complete spectrum of light, and we'd end up seeing white, and that wouldn't help us at all, because that means that every atom in the universe could theoretically emit white light. But the fact that they emit line spectra allows us to gain information about something that we can't touch, like a distant star. Okay. All of this information was combined into an atomic model by Niels Bohr. He was a Danish physicist, chemist. And what he said was, in his model, he modeled his atom after the uh, solar system, where the sun would be the nucleus, and then the places that the planets orbited the sun would be positions for the electrons. And he set it up like this is n equals 1, 2, 3, 4, 5, 6. The lowest energy state in the hydrogen atom is n equals 1. That's called the ground state. And this was his model. Right? Notice that we're missing one of the wavelengths here. Missing the one that goes from 6 to 2. And that produces the line spectrum. Now, Bohr's model was far from perfect. It was a starting point to try to help us understand how the atom is constructed. It was faulty on numerous levels. In the first place, if electrons moved in circular orbits, then they would eventually lose energy because it takes energy to change directions, and they would all eventually fall into the nucleus. They don't do that. So that was one problem with the Bohr model. Let's see. The Bohr model only works for the hydrogen atom, because once you start adding extra electrons out there, then you get those repulsions, and they mess with your energy levels. So the Bohr model only works for hydrogen or atoms that are like hydrogen, that only have one electron in their outer shell. One electron is left. So if we say lithium, which has 3 electrons in the neutral, we would have to get rid of 2 of them. Yeah, we have to get rid of 2 of them, only 1 left. That is, lithium with a 2 plus charge would obey the Bohr model. Right? Circular orbits do not happen. They cannot happen because of the laws of physics. But there are formulas that go with calculating the energy of an electron at any one of these levels, but I thought that was a little too much for this discussion. You'll have to dig that up on your own if you want to know it. Right, and I mentioned the fingerprint nature of these line spectra that help us identify elements. Now, even though the Bohr model doesn't work for polyelectronic atoms, we still get line spectra from the different elements. And that line spectrum allows us to identify elements in distant sources or nearby sources. I used to use an instrument that relied upon emission spectra from various elements, and in a single sample, I could pick out 24 elements and tell you what their concentration was in that sample. Of course, the instrument that I used cost $250,000, so you get what you pay for. Okay, so the last slide I think here is what color of light is emitted when an excited electron in a hydrogen atom falls from a 6 to a 2. That would be the shortest wavelength or the highest energy, because the electron is falling the greatest distance in terms of energy, right? And then the shorter distances give you shifting more toward the red. All right. So that would be the color of light emitted by that falls from the longest wavelength would be the lowest energy. And I think that's the last slide I have. Yes. Okay. So I've said enough on this topic.